Okay, so as I said, I'm going to go through here and show you how this works and how most people go about it. And then I'm going to kind of show you a little bit of a shortcut way of doing it that will work. And it kind of eliminates some of the writing. And I know you guys love that a whole bunch. And some of the work that we have to do. But you'll see that we actually get the same value either way. So let me kind of show you the long version first. And again, this is what you'll see if you watch any videos online. If we're trying to determine the values for which, for example, this power series converges, you might want to rewrite this as the sum as n goes from 0 to infinity of 1 over 5 to the n times x minus 1 to the n. Just make it a little bit easier to see. But either way, what we're going to do is we're going to start by using the ratio test. And for the ratio test, we need to look at the limit as n approaches infinity of the absolute value of the a sub n plus 1 term over the a sub n term. So in this case, that means we're going to look at the limit as n goes to infinity. The a sub n plus 1 term means we just take this, and I probably like this version a little bit better, and everywhere there's an n, we're going to make it an n plus 1. So we're going to have x minus 1 raised to the n plus 1 divided by 5 raised to the n plus 1. And then we're going to divide that by a sub n, which is exactly what you see there. X minus 1 to the n over 5 to the n. And of course, we're going to take that bottom one and flip it and multiply. So this is going to give me the limit as n approaches infinity. Now, I'll still have the x minus 1 to the n plus 1 over 5 to the n plus 1, but let me go ahead and do a little bit of creative math on that as well. Instead of writing x minus 1 to the n plus 1, I'm going to write it as x minus 1 to the n times x minus 1, because that's what it means to be to the n minus 1 plus 1 power, excuse me. I'm going to do the same thing with the 5. 5 to the n plus 1 is equivalent to 5 to the n times 5 to the first. And then I'm going to take this bottom one and I'm going to flip it and multiply, and it becomes 5 to the n over x minus 1 to the n. Well, of course, the x minus 1 to the n's cancel here. One of the 5's cancel here. And we get that this is going to give us the limit as n approaches infinity of the absolute value of x minus 1 divided by 5. And notice here that there's no n's in this. So as n goes to infinity, we simply get the absolute value of x minus 1 over 5. Because there's no n to go to infinity. Now, as you watch the videos, what they're going to do is say, well, this is a coefficient, so we'll bring it out in front and take the limit of what's left. It's the same thing. And remember, by the ratio test, this converged if and only if this absolute value was less than 1. Well, that means that negative 1 has to be less than x minus 1 over 5, which has to be less than 1. And so what we get here is kind of like a three-sided equation. We've talked about this in the past as well. So you have an equation that has three sides. Whatever you do to one side, you're going to do to all the other sides. If you multiply, divide by a negative number, it flips those inequalities, and the goal is to get x by itself. So I'm going to start by multiplying 5 by each and every one of these. So I get negative 5 less than x minus 1 less than 5, and then simply add 1 to both sides, and I get negative 4 less than x less than 6. So this is at least the open interval of convergence. Now, at this point, we would need to check the endpoints, but I'll go into that in a minute. Bottom line is, this is kind of the way that the long, drawn-out method works. All right. Now, I've kind of condensed this a little bit in the method that I've given you. So let's go back and look at what number 2 tells us to do. Okay, if you look at my number 2, it says to use the ratio test, but I'm going to use it only on the coefficients. And the reason that I'm going to use it only on the coefficients is because when I do the x minus 1 to the n plus 1 over the x minus 1 to the n, I'm just going to get an x minus 1 that's going to pull out an absolute value each and every time anyway. So when I do this, and I'm going to take the same problem, and I'm just going to come down the other side just to show you that we get the same thing. I'm going to do the ratio test, but I am only going to consider the coefficient. Remember this form here when I wrote it? Here is your coefficient. So when I look at the limit as n approaches infinity, of the absolute value of a sub n plus 1 over a sub n, I am strictly going to use the coefficients. This is then going to be equal to the limit as n approaches infinity. Again, n plus 1 means we just take this. Everywhere there's an n, we're going to turn it into an n plus 1, and we divide that by exactly what we see. We are going to then, sorry about the screen there, we're going to flip that bottom one and multiply. So this gives us the limit as n approaches infinity of 1. Again, I'm going to take that 5 to the n plus 1 and rewrite it as a 5 to the n times a 5 to the first. I'm going to flip this bottom one, which gives me a 5 to the n over 1. And then the 5 to the n's cancel, and I get the limit as n approaches infinity of the absolute value of 1/5, which is exactly 1/5. Now, what do I do with that? Well, let's look back up at number 2 here, because what I get out of this is what I'm going to call L. Matter of fact, that is what we call it when we do the ratio test. The first two parts work the same whether you do the long drawn out version or the short version. If you get a value of 0, then the radius of convergence will be infinity, and that thing is then going to go on either side of where it's centered, infinity, which means it'll converge for all real numbers. If we get infinity, that means it only converges exactly at r equals 0. Reason being is we're calling r 1 over L. Think about it. If you get 0 and you take 1 and divide it by almost 0, the limit as we get really, really close to 0, you're going to get a value of infinity. Whereas if you put infinity on the bottom of 1, what you get is essentially 0. So it's taking whatever we get there and flipping it to get our value of r. But if we get something in between, then we can define the radius of convergence simply by flipping the value we get. And as a matter of fact, we'll see then, look at the value we just got. We got 1/5, which means our radius of convergence is 5. What does that mean in terms of my interval of convergence? Well, remember that this initial power series was centered at 1, and it was centered at 1 because we had the x minus 1 to the n, and the radius of convergence is 5, so we're going to simply go out 5 units on each side of this thing, and going 5 units on this side will get me to the value of 6. Going 5 units on this side will get me to the value of -4, and well, look at this. We're going to wind up getting the same thing. That is -4 less than x less than 6, and at this point we would need to check the endpoints. So I guess what I really wanted you to see, and we're going to go through and do some more examples so you can see exactly how this works, but whether you choose to do it the long way or using the shortcut that I've given you here, you're still going to get the same result. If you get back a value of 0, you are going to converge for all real numbers between negative infinity and positive infinity. If you get back a value of infinity, then you will converge only at the point in which it is centered. If you get any other value in between, your radius of convergence is the inverse of whatever you just got, and then you just go out that many units on each side of your center to determine your interval of convergence. Again, that's not checking the endpoints, and that's something that we're going to need to do, but I'll get us there with our next video and some more examples.